Welcome to our demonstration of the DEIS toolchain for the European Train Control System. In this demonstration, we will begin by introducing the DEIS research project and its overall objectives. We will then present the Digital Dependability Identity, aka DDI, a central concept developed by the DEIS project. To see how the DDI concept can be used, we will review its application towards the use case of the European Train Control System, also known as the ETCS. In this use case, the integrated development of the ETCS between an OEM and its Tier-n suppliers will be explored and supported by the DDI-based toolchain. In particular, the workflow supported by the toolchain will be presented in detail. For more online resources regarding DEIS, DDIs, and the tools presented next, please refer to the links at the end of the presentation. The Dependability Engineering Innovation for Cyber-Physical Systems, also known as the DEIS project, recently successfully concluded. The project involved several partners across Europe, from Ireland, the UK, Germany, Austria, Italy, and Turkey. DEIS aimed to support the development and application of cyber-physical systems through the concept of the DDI. The project identified benefits both towards improving development efficiency as well as integrating heterogeneous CPS at runtime. To achieve its objectives, the consortium developed the concept of the DDI, established semi-automatic methods for generating and integrating them from CPS, developed tools for automated CPS integration in the field, and applied the above in industrial use cases. DEIS explored its methods and tools with use cases from the automotive, railway, and healthcare domains. Large cyber-physical systems often form hierarchies of constituent subsystems. Managing the development, deployment, and interaction between the subsystems and assuring the dependability of the overall CPS is a major challenge. We address this challenge by combining dependability artifacts into the machine-readable DDI and associating it with a CPS element during development. As development progresses, other CPS elements with their own DDIs can be smoothly integrated. This process spans across the development lifecycle, from design to configuration to operation. When we consider a generic CPS, it may consist of multiple subsystems, each further involving several components. The DDI of the CPS expresses its dependability aspects, as seen here. Each of the CPS components may also feature its own DDI, representing the component dependability properties. The DDI of a subsystem can incorporate the DDIs of its constituent components. In turn, the CPS DDI can also incorporate its subsystem's DDIs. To assure the dependability of the overall CPS, DDIs offer the viewpoint of the assurance case. An assurance case presents a combined argument explaining how the CPS is dependable based on patterns informed by standards, such as the V-model development lifecycle, and evidence derived from dependability artifacts, such as the system design, hazard and risk analysis, and failure models. To support the information integration of all the above concepts, the DDI is specified using the Open Dependability Exchange, also known as ODE metamodel. The metamodel integrates the ACCM OMG metamodel for structured assurance cases, as well as domain-specific metamodel packages for system dependability properties. In the future, we will look to further extend the metamodel to link with similar initiatives, such as the AMAS project's Common Assurance and Certification metamodel. To illustrate how all this ties together, we will discuss the ATCS case study. One of the challenges that the ATCS aims to address is seamless operation across national borders. To achieve this goal, the equipment on board the train must interoperate with trackside equipment. Therefore, smooth integration between the two sides is key. Movement under the ATCS is tightly controlled by a movement authority, with the ATCS monitoring and enforcing the authorized movements. Here we see an overview of the ATCS architecture, consisting of the two main elements, the onboard unit at the top and the trackside at the bottom. We envision that an OEM could distribute the development of each part to one of its suppliers. As each supplier provides its results, it is then up to the OEM to integrate and validate the complete system. To demonstrate this scenario, we have assigned the two suppliers and the OEM different modeling and dependability tools developed by the consortium partners. Each partner tool produces models for its corresponding part of the ETCS and exchanges it with the others. DEIS developed a common tool adapter to support this process. The common tool adapter offers a generic interface for tools to more easily import and export DDIs. Furthermore, it is extensible, thereby allowing other tools to also use its services. Our common tool adapter is based on the Apache Thrift framework. The framework supports flexible and language-agnostic inter-process communication, alleviating the effort required to communicate DDIs across tools developed in different programming languages. In a typical development scenario, different suppliers can provide the OEM with their design and implementation for separate elements of the architecture, with the OEM being responsible for their integration. In the scenario we explore here, DDIs can be used to allow each supplier to seamlessly use their own toolchain to provide their results to the OEM. We begin the process by looking at the modeling of the trackside using the Composer tool by Siemens. As a supplier of the ATCS trackside equipment, we use Composer as a tool for both the model-based system engineering and the safety engineering. The trackside subsystem consists of a Eurobalise, a Euroloop, and the line-side electronic unit, or LEU. The Euroloop consists of the loop modem and the Euroloop leaky cable, or ELC. For the safety analysis of the ATCS trackside systems, a component fault tree, or CFT, is created. A safety argumentation is created using the goal structure notation, or GSN. The GSN argumentation consists of two parts, a process-based and a product-based, and explains why the ATCS trackside subsystem is sufficiently safe. To exchange the safety-related information with the OEM, we create a DDI file. The DDI file consists of the information about the system design, the safety analysis in the form of a CFT, and the safety argumentation in the form of a GSN. As the ATCS trackside equipment supplier, we don't want to reveal details about the subsystem to the OEM, which is why we create a black box DDI using automated scripts. As a first step, we create an empty DDI file. Then, we use the script execution capabilities of the DDI Common Tool Adapter to run a script which creates a black box DDI based on the information exported in the DDI file. The black box DDI of the ATCS trackside subsystem consists only of the information necessary for the OEM to create the safety case and does not reveal details about the implementation of the subsystem. To hand over the DDI to the OEM, we copy the file on a USB stick. Next, we will see how the HipOps tool from the University of Hull can model the onboard unit. In this part of the demo, we will see how to model one of the ATCS subsystems with MATLAB Simulink and HipOps and export the DDI from it. With Simulink, we can easily drag generic subsystem blocks to compose our system. We can easily compose subsystems by linking their I/O ports. When we want to begin annotating our model with failure logic, we invoke the HipOps utility from the MATLAB command line. To annotate the failure logic on our more complete model, we first select the specific element we want to edit, then we choose to edit the current block's failure data from the dialog. We select the default implementation to edit its failure data. We see numerous possibilities here. For now, we will just review how output deviations of the given element are defined. Here, we can define how the given element can fail given a combination of its internal failures or inputs. The selected element did not happen to have output deviation logic defined here, but we will see how this can be defined for other aspects soon. The user repeats the process for another element, this time inspecting one of its basic events. This basic event has a constant failure rate model set and a specific failure rate. We can review the output deviations of this element once more to see how its failure logic is defined. We see the logic captured in the expression and can edit it. The output deviation uses a logical OR to require a basic event internal to the element and an input event to be triggered. At this point, modeling and failure logic annotation is complete, and we can now perform automatic fault tree analysis. After a few moments, the results can be seen on a browser window. The fault trees analyzed can be reviewed in depth as well as the minimal cutscenes. Additionally, FMEA results, including direct effects, further effects, a combined view, as well as events causing no effects, can be seen. The results have been stored on the local disk. To convert to DDIs, we first launch our common tool adapter. Now, we can execute a command line utility to convert our models and HipOps results into DDIs. Our models and results have now been converted into DDIs. Here, we see how a DDI looks like in its XML-based format. We can see the DDI includes the fault tree analysis results and the specific deviation we saw earlier, as well as the system itself. At this point, the safety box tool from Fraunhofer IESE can be used by the OEM to combine the subsystems provided by the suppliers. As safety engineers, we use SafetyBox as a tool for modeling the safety argumentation for the ATCS onboard system. SafetyBox supports GSN for building up a model-based safety argumentation. GSN is used to decompose safety goals into safety requirements via structured argumentation, also known as strategies in GSN, that are supported by evidence, also known as solutions in GSN. For semi-automatic integration of the onboard system's architecture, failure logic, and safety argumentation, we export the safety argumentation into a DDI file. The GSN elements of the safety argumentation are transformed into the DDI representation, an assurance case. At this point, the DDI fragment containing the onboard failure logic and architecture specification can be transferred to us via USB to integrate with the safety argumentation. We have received the DDI fragment containing the architecture and failure logic of the ATCS onboard system from our supplier. For integrating the GSN DDI fragment and the architecture and failure logic DDI fragment into one ATCS onboard system DDI, an empty DDI file is created. The integration is performed semi-automatically by executing a script from within the SafetyBox tool using all three DDI files. After the script execution, the previously created onboard DDI file now contains all three artifacts. At this point, both suppliers have already generated a DDI of their subsystems. The ATCS integrator created an ATCS container DDI at the cyber-physical system level that is used for integrating both the trackside and the onboard subsystems into one combined ATCS system. The integrator receives the DDIs from the suppliers and integrates them into one ATCS DDI. The integrator has designed an ATCS model on the system level for further integration. The ATCS model is exported into a DDI file containing the failure model container, the architecture container, and the top-level safety argumentation. A new model file is created, which in the end will contain the integrated ATCS model. Next, all received models are combined into the newly created file using a script. As a final step, another script is executed to perform internal remapping and binding in the final ETCS model. As a result of the process, the ETCS model contains the integrated architecture, the integrated failure logic, and the safety argumentation of the subsystems, as well as the overall ETCS system. As a system integrator, we want to perform a fault tree analysis on a DDI model without importing it into our modeling tool in advance. To achieve this, we execute a script via the common tool adapter using the integrated DDI. The following steps are performed automatically. The script calls an external service that executes the actual FTA. In this example, the service is provided by the SafetyBox fault tree analysis backend. After the FTA, the service returns the result to the script running on the tool adapter. Finally, a new DDI file is generated, which contains the FTA result. Having a new DDI containing the FTA result, we also want to validate the result to confirm whether it matches the expected failure rate. Therefore, we execute another script on the tool adapter outside SafetyBox. The script returns the validation result back to SafetyBox. In order to let an external service perform the FTA automatically, and afterwards validate the FTA result, some formalized information has to be provided within the ETCS DDI. Within an argumentation goal, the following formalized information is provided. First, an activity tag with the value quantitative FTA. Next, the target failure rate, with the resulting failure rate from the analysis being validated against it. Finally, the top event that shall be analyzed. In addition to this, the top event must be defined in a failure model. As a preparation for the automatic fault tree analysis, we first create a new empty DDI model file, which will be filled by the script. The script is executed from within SafetyBox. After the FTA, the previously created DDI model file now contains the whole ETCS model, including the determined failure rate for the analyzed top event. To validate whether the determined failure rate is below or equal to the required failure rate, another script is executed to compare the new added failure rate against the required one in the DDI model. Now that the ETCS system and its failure logic has been integrated, its assurance case must be integrated as well. This is feasible using the Acme tool by the University of York. At this stage, the final assurance case of the ETCS must be composed. To do so, the GSN fragments contained in the integrated DDI must be converted into their structured assurance case metamodel, or SACM, equivalents. The Epsilon Transformation Language, or ETL script, on the left panel can perform this conversion. The script contains rules for converting each of the GSN element types it encounters in our provided DDI into its SACM equivalent. We execute the script via the Eclipse IDE. The script has successfully converted the model elements. On the right, we can view the initial source DDI that we provided from the previous steps in our process. Now, we can review the converted DDI containing the newly created SACM elements, for instance, the overall assurance case package, the ETCS argument package binding, and the ETCS onboard argument package. Acme is a plugin for the Eclipse IDE which allows us to review the completed assurance case graphically. We can start by either creating or opening an existing assurance case diagram in Acme. This one already has the ETCS assurance case loaded, so we'll remove it and now show how to import it. We use the import feature and select our converted DDI, listed as the output.model here. Our assurance case is now ready to be reviewed. We can do so by navigating into its internals. We can see its composing elements here. For instance, the onboard argument package interface, and the Atcs argument package binding, which requires relayouting when loaded. Luckily, that's easy enough. As we can see, the binding provides the overall framing for the Atcs assurance case, linking the onboard and trackside argumentation together. For our example, the reasoning here is kept simple, but more detail can be added at the user's desire, using the controls on the right panel. Moving on to review the onboard argument package, we lay out the diagram, as we can see, this mirrors the GSN argumentation shown before in the safety box tool. After loading the relevant diagrams, the user can navigate through them and follow the argument flow. For instance, we can move to the onboard argument package interface, and from there to the onboard argument top-level claim. The assessor has now completed the review of the Atcs assurance case. At this point, the Atcs system and its dependability artifacts have been integrated. Furthermore, we have shown how appropriate validation checks to support the assurance case of the system can be automated. For further information on DEIS, DDIs, and the toolchain presented here, please visit the DEIS project website and our open source GitHub repository. Finally, we would like to acknowledge the EU Horizon 2020 Research and Innovation Program, as well as our consortium partners for helping bring DEIS to fruition.